So we're going to pick up in section 13.4 where we left off last time. I believe that we had stopped with creating a box plot. Does that sound right? Yeah. Excellent. So our box plot looked like this when we were done. We talked about some of the benefits that we can see how the data is sort of grouping together, especially if the data was more than 7 points. But we also talked about sort of some of the drawbacks that we lose the specificity of exact values that are showing up. Even the specific like locations where we have the vertical marks and the dots on the end. The dots on the end are part of our data set, but those vertical marks wouldn't have to be, right? Q1, Q2, Q3 could be values that are in between other values if there were an even number of values and things like that. So we lose some specificity. So this gives us a big picture though. It gives us a big picture of the data set. It shows both the extreme values, it shows how values bunch up, and it shows how they're sort of divvied up as well. As we're moving into the rest of what we're looking at for variations specifically, we're going to take a look at only the how they vary part of it. So the first thing, this is deviation. The first one we're going to look at is called mean absolute deviation. This one makes use of absolute value to find the difference that each data point is away from the mean. It's found by taking all absolute value differences and averaging them together. We're going to do an example of this, but I want this one alongside the other deviation in your notes. So we're going to look at that one second, and then we will actually do each of those features with the data set we've been working with. Okay, are we good to slide to the next slide? Okay, so variance and standard deviation are actually the other type of deviation. So to find variance, we find the mean. We subtract the mean from each number. We square the differences that we got in step, that should say step 2. It's a typo. And this one should say step 3. Okay, so we square the differences from step 2. We find the sum of the squares in step 3. And then we divide by the number of values. That's a typo on your book, on your pages I printed too. Double typo, man. Okay. Standard deviation is almost like step 6 to this. So if I want to find the standard deviation after I've already found the variance, I just need to take the square root. It's essentially step 6. Standard deviation is something we can use and will use. Variance, however, is not actually a feature that we gain much information from unless we move on to standard deviation. But it does have its own name. We're going to do some examples when we get to chapter 14, not examples, but you're going to see an example in chapter 14 how the standard deviation is used with something later on. But first, we're going to take a look at simply how we find standard deviation and mean absolute deviation. So we're going to use that same, this data set, you're tired of it, I know. But this is the same data set we've been using, right? And we're going to find the mean absolute deviation. Now, for both mean absolute deviation and standard deviation, we need to find the mean. And we already did that on this data set. Can you guys flip back and tell me what was our mean for this data set? We did it at the very front page. It was 19.9. Okay? So if we hadn't already found that, we would do that. Remember, mean is found by adding all the values together, dividing by the number of values. Okay, so this is our mean. So to find the mean absolute deviation, which we will abbreviate as MAD, we are going to take each, I'm going to call them score, it's our number of values, and we're going to take each of those values, which I'm going to call X, and we're going to subtract the mean. And when I do it, I really don't care if it's positive or negative. Hence, absolute, right? It's the absolute values. So I'm going to find the absolute value of the difference. So I'm going to write all these values down. I'm just going to write them in the order I was given. You can write them in numerical order, smallest to largest if you wish. It looks something like that. So we're going to take each value. I'm going to write the first couple in. Maybe I'll write all of them in for this one. We're going to take each value and we're going to subtract the 19.9. So how far apart are 18 and 19.9? Don't overthink this. How far apart are they? What is it, Abby? 1.9. Now, technically, it would be 1.9 and then we take the absolute value. Okay, fine. But the point is, that's how far apart they are. How much does it differ? How far are they separated? We're going to do the same thing with 22. What is 22 minus 19.9? And then the absolute value. 2.1. If you're struggling to do this in your head, grab a calculator.
How is that 1.9?
Because we're subtracting 19.9 minus 18. This is 1.9, right? Anytime we subtract integers, we just take the bigger number minus the smaller number, and then the sign would be negative here. But then I'm taking the absolute value anyway. The absolute value would give me the positive part. So the second one's 2.1. Is that one okay? Okay. That must mean the third one's 2.1 because, it's the same. The 17 would be 17 minus 19.9. What's that one going to give me?
2.9.
That one's 2.9. And then I have, hey, this one already did, 18, right? I already did this one, so I know this one's 1.9. And then, do I have them all there? 1, 2, 3, 4, 5, 6, 7.
There's 30.
I missed something, the 30. I did miss the 30. I think I have them too close together. Let me move them down a little bit. 30, 12. Okay, just a little too close together on my screen. 30 minus the 19.9. What's that one? 10.1. Then I have the 18, which I knew was 1.9. The last one is 12 minus 19.9, 7.9. And you don't have to show this work right here, this subtraction. That's fine. I don't need to see that. You can use your calculator to find those, and then you're finding the absolute value. Okay? So a bunch of values, 1.9, 2.1, all the way down. And what the mean absolute deviation does is we take the sum of those values. So somebody, please, if you don't have it out at this point, grab a calculator. Let's add all of these values together. Sum. Mm-hmm.
In between those sides. Sorry.
Okay, so what is the sum of those values? Did we get it yet?
28.9.
That's what I have as well. Thank you, Savannah. 28.9. And then the way that I get the mean absolute deviation from that is I take that sum and divide by 7 because I have 7 values. So what is 28.9 divided by 7?
4.13.
Yeah, we'll do one decimal, kind of like what we were doing last time. So I'll do 4.1. Thank you, Wiley. Okay, so 4.1. That is our mean absolute deviation. Okay, is that okay? Standard deviation starts out the same. Okay, now this one actually says variance. Okay, notice part C is going to say standard deviation. It's just going to be one additional step. But finding these two things starts out the same. We're going to create a chart. We're going to try and make it big enough this time that I can actually see my line separations. Okay, so we have all of our x values. I'll just label it x this time. 18, 22, 22, 17, 30, 18, and 12. That's much better. And in this step right here, I want them subtracted, and I don't really care about the sign. So if you want to call it the absolute value, that's fine as well. We already did these steps, so I'm going to write them in from our previous screen. I had 1.9, 2.1, 2.1, 2. 10.1, 1.9, and 7.9. Okay, so it's just hangover from the previous thing, right? Just pulling it through. So if we're taking a look, I promise I'm going to come back to this slide, but the list of things we've done, we've got the mean, we've subtracted the mean, we're on step 3, which is to square the differences. That's our next step. Let me go back to where you guys were. So we're going to take each of those values and we're going to square them. Okay? So, what is 1.9 squared? What you got, Aubrey?
3.61.
3.61. Is that okay? All right, what is 2.1 squared? 4.41. Okay, now we're all with this. The next one's also the 4.41. What is 2.9 squared?
8.41.
Thank you, Micah. 8.41. What is 10.1 squared? This one's larger, much larger. 102.01. But 1.9, we already did that one, so that was 3.61. And 7.9 squared.
62.41.
Okay, everybody good? Squared a bunch of values. And then we're going to add these together, just like we did on the previous, right? We're going to find the sum. So what do we get when we add these all together? And 88.87. Fantastic. And then our last step on that list of steps is to take that 188.87 and do what? Divide by 7, because there's 7 values. So this is going to give us our variance. What do we get?
21, 30. I guess we're 26.9.
Okay, 26.9. I have 27 written down. Is it rounded?
It should be 27.
Okay, is it rounded to 27? I might have written it down wrong. 27, so I'll just write 27.0. Okay, so this is the variance. Notice that's nowhere close to the mean absolute deviation. But the reason is because the mean absolute deviation corresponds to the standard deviation, right? Those are values that are going to be close. And all I have to do to find the standard deviation is to take the square root of that 27. So what is the square root of 27? With 1 decimal will be good. Thank you, 5.2. So that is our standard deviation. Now the standard deviation, the standard deviation actually plays into the next distribution that we're going to look at. Well, it's only distribution we're going to look at, but it plays into the normal distribution. Okay, it's a connection point before we do. Yes, Savannah?
So the first part that we did, like part A, was that like its own thing, or did
Yes.
you just do that when you
Yes, it was its own thing. We had a slide over here that talked about mean absolute deviation. It's its own standalone. Yeah, mean absolute deviation is one way of looking at how far the data is spread apart. Standard deviation is another way of looking at it.
Okay, so they're not always together.
No, but the chart looks very similar, right? The only part that's different is what happens after this, right? This part of the chart matches. Standard deviation just keeps going with more pieces of information.
But variance is always with standard.
Variance is part of standard deviation. Yes, those two are going hand in hand. Yep. Okay, all of this relates to what are called normal distributions. So let me describe what a normal distribution is and the fact that you've seen this before. You just didn't know it. A normal distribution is a smooth bell-shaped curve that depicts frequency values distributed symmetrically around the mean. And when you have a normal distribution, the empirical rule will apply. The empirical rule says that if you have 1 standard deviation away from the mean, you have 68% of the data in that area. And if you go 2 standard deviations from the mean, you have 95% of the data in that part of the space. And if you go 3 standard deviations from the mean, you have 99.8% of the data. Okay? So I want to draw you a picture on this one, and you can just put yours in on the side a little bit. Mine will go on the bottom because that's where I have space. But it looks like this, roughly speaking. You've probably heard grading on a curve before. It's not what you think it is, by the way. It doesn't mean everybody just gets bonus points added on. Grading on a curve literally means taking the average that everybody gets and putting it right here. And this is the mean, okay? X bar right there. And then it means making sure that if I go 1 standard deviation in each direction, I will get 68% of the data. So this is 68% in between here. Goes from here to here. Okay? So if you can imagine this piece right here being 75, right? Think about it like an averaging score, right? 75. Going up a little bit, maybe it's an 80. And maybe it goes down to what did I do, 80, 70, okay? Maybe. Or maybe it doesn't. Maybe everybody did really, really good on the test. And so now the mean is an 80. So the 80 is right here, and all of a sudden an 80 is a C. What do you think about that? That's actually what grading on a curve means. It means normalizing a lot of data. It doesn't work very well for small groups. But I will tell you that when I was a grad student and we were looking at a classroom of 500 students, we talked about it. We had a trig class. It wasn't a class of 500 students, but it was all the classes of trig. And we looked at the scores, and we normalized the scores when we were done and said, what's the median in the middle? What is the mean in the middle? How is this data distributed? What should our center value be? If everybody did bad, grading on a curve is yay. If everybody did good, it might not feel so yay. And then if we go out, I'm going to change colors so that we can distinguish. We'll use red. If we go out 2 standard deviations, this piece right here in red, okay, all of this, would be 95% of the data. And then if we go out 3 standard deviations, we'll do purple, all the way from here to here would be 99.8% of the data. It's almost 100. So when a company is mass producing something, think cereal boxes. So if you get your cereal box, it tells you how many ounces are on the bottom of your cereal box, right? Okay. Did you know that if you measure out that cereal, it might not be exactly that number? There's some measure of error that they're allowed to have. But the average has to be whatever it says on the bottom of that box. 68% of the boxes are within 1 standard deviation of that, and then 95% and then 99.8%. So you may have a 15-ounce cereal box where there's only 14 ounces in it. I don't think that means you should take your scale to the grocery store, but it's actually correct, right? Like it doesn't have to actually be that value. So let's take a look at some examples so you can see how it actually plays out, how it works. It says assume a normal distribution. It matters that this phrase is here. If this phrase is not here, nothing else works. Nothing else works, okay? You will see it in all the problems you're working in. It's going to be there. But if it's not there, the empirical rule doesn't apply. Nothing else actually works. It's got to have that phrase in there. Assume a normal distribution, that the average phone call in a certain town lasts 8 minutes with a standard deviation of 2 minutes. So we're going to start with this data, and we're going to create the normal distribution bell curve to see what it looks like, and then we'll be able to answer the questions that were asked. So I'm going to draw this in. Our mean is what they gave me. It's 8. The standard deviation means that I take that 2 minutes from the middle 8 and I go 2 to the left and I go 2 to the right. So what is 2 to the left of 8? 6. Don't overthink this, right? What would be 2 to the right of 8? 10, thank you. And we're going to do it again. So this is 1 standard deviation. I need 2 standard deviations now. So if I go 2 to the left of 6, I get 4. And 2 to the right of 10, 12. We're going to do it one more time. 2 to the left of 4, 2. And 2 to the right of 12, 14. Okay, this is actually what we need. I'll see if I can get it to work. I've been having struggles today with my my tools. Okay, this is the chart that we're going to have and use for every single one of the questions that are asked about this data. Okay, this is the same picture I'm going to draw. Okay, so this one says we want the percentage of the phone calls that lasted between 6 and 8 minutes. So between 6 and 8 minutes is here. So when you're doing these problems, I expect to see a bell curve with something shaded in. You got to draw it. In part because I want to make sure that if you make an error, I can figure out what the error is and we can have a discussion about it, right? Okay, how can I figure out what the area is in that shaded region? Okay, you're right. It's half of 68%. How did you get that, Abby? Fabulous. So if I went all the way from 6 to 10, by the empirical rule, that would be 68%, right? But I don't go all the way over to 10. I stop at 8. So it should be 68% divided by 2, and I will have 34%. So with this information, 34% of the phone calls would have lasted between 6 and 8 minutes. Okay, is that good? Okay, let's try another one. Same information, different question. Well, yours is on the same page. So I'm going to keep putting mine in here, at least in theory. We're going to try and see how this works. Oh, look at that. Tools are working in this class. That's good news. Okay, this one says we want the phone calls to last less than 4 minutes. So here's my 4. I wanted a color. 4, and we want it to go all the way over here to the left. How am I going to figure out the phone calls that lasted less than 4 minutes? It's not in the middle. The last one was in the middle, right?
Don't you take like either? Don't you take a third of 99.8?
It's not a third of 99.8, but we are going to use the empirical rule, but not quite like that.
Well, a fourth.
Okay, where did you get 5 at, Abby?
No, I know it wrong. But
You're close.
there's the 95% that starts at 4 and put it into 12. So we'd actually have to subtract more than I'm subtracting. There's 5% or half of 5% on the other side.
Okay, pause for just a second. Does everybody see where she got the 95%? Is everybody good on that step? Okay, so Wiley, she got the 95% because 2 standard deviations to the left and to the right for the empirical rule is 95%. So she's using that empirical rule and identifying that 2 to the left is 4 and 2 to the right is 12. So this part of the graph is 95. Okay, does that help? So if it's 95 that's sandwiched in between my 2 red lines, how much is on the outside pieces? That's 5. So these 2 pieces on the outside combined total are 5%. That kind of looks like a 50. Let me try that again. That's better. 5%. But I don't have both pieces, do I? So what am I going to have to do to find just the piece over here on the left? Half it. I have 5% divided by 2, 2.5%. What do we think? Probably more practice, right? Yeah, it's okay. Let's try another one. Okay. This one identifies that I want it to be more than 12. What would more than 12 be? I'm pretty sure Abby already knows. What do you have, Addie?
Would it just be 2.5%?
Yeah, it's the other half that I didn't have last time, right? It's just the top half. Not half, but the top part, the top portion that I didn't have before, whereas last time I had the bottom portion. So it's 2.5%. Let's change contexts, okay? Okay, so this was a phone call one. Did you know your standardized tests do this? That's a legit thing. And so standardized tests, this is the mean IQ scores for 1,500 students is normally distributed. Do you see that phrase again there? If they don't tell you normally distributed, you can't use anything we're working with. They'll tell you it every time, but I want to make sure you understand it matters. With a mean of 100 and a standard deviation of 15. So we're going to start with our picture. Our picture does not have to be great. It just needs to be a shape, okay? Just the basic shape. It says that it's a mean of 100. And I'm going to go 3 in each direction. How much am I going to, let's do the part that's on the right-hand side. How much am I going to add to the 100 to get my next hash marks? 15, because it says standard deviation of 15, right? So the first one, 115. What's the second one? 130. And then 145. Fabulous. Let's go the other direction. I'm at 100, and I need to subtract 15 now. So what will you be if I go backward? 85. And 70, and then 55. Okay. Now we can look at the questions. The first one asks us to find the IQ between 85 and 115. So it's this part shaded in, right? Now, we know the percentage. That's straight out of the empirical rule. What does the empirical rule tell us this percentage is? 68%. Okay, everybody good so far? That is not what the question asked. What did the question ask? How many students? And a percentage is not what it asked. It wants a number of students, like people. So if I know I need 68% of my students, there's a couple of ways I could find the actual number of students. Somebody tell me one of them.
So do 1,500 times 0.68.
Okay, that's one way, yes. So I could take my number of students and I can multiply by 0.68. This is the most straightforward, direct. Let me show you the other one. As a reminder, we did percentages, right? Where we did 68 over 100, and we do x over 1,500, and we set it up as a proportion. If you like the proportions, you could do it from this perspective. Okay? Addie mentioned the 1,500 times the 0.68, so that's what I'm going to go with. What is 1,500 times 0.68? 1,020. And this is students, right? I didn't have to label phone calls on the last one because it was a percentage. The units were percentage. These units are students. Let's do another one. Same context. It says over 145. So here's my 145. It's over here. What am I going to do to get over 145? This looks and feels a lot like our over 12 and under 4, I think it was, from our last problem.
Did you just do, take 2.5% of
So not quite, because we're over here at 3 standard deviations instead of 2, and on that other one, we were at 2 standard deviations. So what are we going to have to adjust?
0.1%, so half of the leftovers from 99.8%.
Okay, so let me draw it in what you're describing. My red marks now are identifying 3 standard deviations away from the mean, right? What does the empirical rule say that the percentage is between 3 standard deviations away? 99.8. So if I have 99.8, I need to take that away from 100, and I would get 0.2%. That is not 2%, that is 0.2%. So these pieces here and here are 0.2% combined. So how much is it in this space only? 0.1%. So that's the value that I need to actually multiply by 1,500. What is 0.1% in decimal form? 0.001. Got to move the decimal twice. 0.001. What's 1,500 times 0.001? 1.5. Can I leave that as my answer? Why not? No cutting students in half. Bad practice, right? Not going to do that. So we're going to use just regular rounding rules. Don't overthink this. Just go with your regular rounding rules. This would be how many students? It's 2 students, about 2 students. Okay, so we're going to down to 2 students then. Okay, I think we have one more question on the normal distributions, and then we'll pick up next time with the rest of this section. Same information, but this one is asking us to go from 70 to 145. This is a little awkward. Why? Right. I'm 3 standard deviations on the right, Savannah? and I'm 2 standard deviations on the left. So it's not one of the numbers from my chart, but I can still use the numbers from the chart to figure out what it is. How would I do that? Any thoughts?
Find it for the second and then add on the half of the third.
Okay, so if I find it for the second, like this, what would I do next, Megan?
Then get the other one for the third.
Okay, how much, I meant to say, what is the value between there first?
The 90.
That's 95%, yeah. So this one's 95%, but it's not all of it, right?
Yeah.
I need to figure out what it is for the third as well. So let's do that one. Let me change colors. Let's do blue. We haven't done blue yet today. If I go this part, I get 99.8. So I can take the 99.8 and the 99.5, and what do I need to do with them? I need to subtract them, yeah. So I need 99.8 minus 95, which will give me what? 4.8%. And that 4.8% is this area right here, in between 55 and 70, and in between 130 and 145.
So would you half that again?
So I would half it, you got it. So this 4.8% needs to be halved to give me 2.4. So what percentages am I going to add together now?
Wait, I'm sorry. 2.4. Why did you have the 4.8?
Because I only have one of these two spaces, this one and this one, so I halved it. Yes. Okay, what was that then?
Then would you add that 2.4 back in the 90?
To the 95? Yes. So the 95, right, from red to red, plus the 1/2 piece over here that I got was the 2.4. This is 97.4%, correct? Am I done? No. I was supposed to find numbers of students. So I have 1,500 students. What am I going to multiply by my 1,500 students? 0.974. What does that give you? $14.61, is that what you said? Yeah? Okay, I got a nod, good. 1461, what? Students. 1,461 students. Okay, so I'm going to stop the video.